once again, we have a section which is glorified calculus. Well, okay, not glorified per se. It's basically just before calculus, just short of calling it calculus. Why? What happens when you take a curve, make a secant, and make the gap smaller and smaller around, say, a point? Well, sooner or later, you end up approaching infinitely close to the slope at that point. Now, what is the slope at that point? It is the instantaneous rate of change, which is defined ever so helpfully as the change that takes place in an instant. As you can probably tell, the textbooks do not amuse me very much. But anyhow, this does work. Why? Oh, it's a slope at one particular point of a curve. The slope as the next point over has changed, and the next point change. Well, obviously, if we need to find the slope of a tangent line, we need to find the slope at that one point. So how can we find this? Well, we can take secants that get closer and closer and closer. So here, by the way, please note that these instantaneous rates of change, depending on what units you're actually looking for, you might have to change the signs. Why? Say a person is measuring your approach to them with a radar gun, and they measure that it's whatever function, okay? And you're getting closer and closer to them. Obviously, the distance to them is going to end up traveling downward. So negative on a graph. So negative slope. Wait a second. You're in the car. You look at the speedometer, so the thing that indicates your speed, and guess what? That is not negative. So there's a bit of a, hey, what does running at 30 meters per second mean? Well, first of all, that means you're not superhuman, or not human, but that's another point. So running at 30 meters per second, hey, wait, which direction, really? Because that makes a big difference, right? So 30 meters per second up is a lot more impressive for running than 30 meters per second sideways. I mean, of course, unless you're running up ladders, but even then that's impressive. So y is t squared. So y for 3 is 9. For 2 we get 4. For 2.001 we can do this by hand, but too lazy. 2.1 squared. 4.41. 2.01 squared is going to be 4.0. Yep. 0401. And 2.001 is going to be 4.004001. Delta t, change in time, is 0.001. And here, well, delta t is 0, delta y is 0. Because this is the point we're looking at. T equals 2. Sometimes you might want to make a little marker on, say, a table like this to remind yourself what your baseline is actually supposed to be, or what you're trying to reference for delta t and delta y. So delta y is going to be 0.004001. 0.01, 0.1, and 1. Delta y here is going to be 5. And here, 0.41, 0.0401. Delta y divided by delta x. Well, here we have 5 initially. And then we go down closer, and we get to 4.1. And we get even closer, and we get 4.01. And then we get even closer, and 4.001. And lo and behold, I think we can all probably guess that the next one's going to be 4. So our estimated instantaneous rate of change is 4. Now, if we had calculus knowledge already, we'd actually be able to confirm that this is correct. Now, we're welcome to also do it from the other side, but we will converge at the same conclusion. Instantaneous rate of change. In this equation, find the instantaneous rate of change at x equals 3. This is the slope of the tangent line at x equals 3, or m3. How can we find this? Let h approach 0. So, what we're looking for is slope of secant from x equals 3 to x equals 3 plus h. Now, what does this actually do for us? M3 equals f of x plus h minus f of x over x plus h minus x. So rise over run. I think we're all familiar with rise over run, yes? So what actually happens here is x plus h 5 times x plus h squared minus 5x squared over h. Now, we will get 5 times x squared plus 2xh plus h squared. And this is minus 5x squared. So, this is all over h. Thus, we will end up with 10xh plus h squared, because the 5x squared and minus 5x squared cancel. Oh, plus 5h squared, not that it actually matters, as we'll notice in a very brief moment. And we end up with 10x plus 5h as h approaches 0. So this is approximately 10x. Well, actually, there is nothing approximate about it. Why? Because h is approaching 0 from both sides. And the actual slope of m3 is not approximately 10x, it actually is 10x. Now, as we can see, that actually relates to this. It relates to it in a very specific fashion, which we'll learn more about in derivatives. Now, wait a second. What are we actually looking for? We're not looking for a formula for this thing. We're looking for this. So while we hammered out the general formula, what do we have to do next? Well, of course, substitute in x equals 3, right? So, equals 10 times 3 equals 30. Now, wait a second. Is there anything particular about this problem? So is there any context that we're given about this problem? No. So that's why we have no units. So the instantaneous rate of change at x equals 3 is M3 equals 30. There, that's our statement. Now, calculation of the general formulas for tangents can be done in this fashion, as long as we have the initial formula to start with. The actual calculus, which is much faster, is learned rather later. Although this basically represents the origins of calculus as we know it. When people figured out that there were a pattern to these things, and hey, why don't we just use a pattern? Come on. Why? Because people are lazy. Lazy people made the world. Like the wheel. That was a guy being too lazy to carry his stuff. So, or alternatively, to actually spend the effort to make his clay pots better without spinning them around. Well, anyhow, ancient history aside, that's actually it for this section. It's also it for this chapter. And, well, we'll see each other again then, next section and next chapter.